Welcome. Settle yourself comfortably now. Let the day's concerns drift away like mist. Tonight, we're going to follow water on its long, patient journey, from the cold depths of space to the gentle waves lapping at Earth's shores. This is a story measured not in days or years, but in billions of years. A story of molecules that have traveled farther than you can imagine, transformed more times than we can count, and finally found their way to the world you call home. Close your eyes if you wish. Breathe slowly. Imagine yourself floating, weightless, surrounded by the most familiar substance in your life, water. The same water that fills your glass, falls as rain, flows in rivers. Water that has been part of comets and asteroids, locked in ancient rocks, exhaled by volcanoes, and cycled through countless living things. You are made mostly of water. Your body is a temporary vessel for molecules that have existed since nearly the beginning of the solar system. Every breath you take contains water vapor. Every cell in your body floats in water, uses water, depends on water. Tonight, we'll trace water's biography, not with drama or urgency, but with the calm patience that water itself teaches. Water is patient. It waits, it flows, it changes form but never truly leaves. It is the most persistent traveler in our solar system, and the most essential ingredient for the life you know. Let your mind drift now, back through time, out into space, to where water's story begins, in the cold darkness between stars, where the solar system was nothing but a slowly rotating cloud of gas and dust. There's no hurry. Water has waited billions of years. It can wait while you relax, while you let go of tension, while you allow yourself to drift into the gentle current of this ancient story. We begin in ice and darkness, in the depths of space. Imagine yourself, though you have no body here, no form, suspended in a vast cloud of gas and dust. This is the solar nebula 6 billion years ago, before there was a sun, before there were planets. Just a slowly rotating cloud of material, the remnant of earlier stars that lived and died before our solar system was born. The temperature here is unimaginably cold, nearly absolute zero, just a few degrees above the temperature at which all molecular motion ceases. In this cold, water cannot exist as liquid. It exists as ice. Individual molecules of H2O frozen onto tiny dust grains, forming thin coatings of frost on particles of silicate and carbon. Look around this cloud. Though looking isn't quite right, since there's no light to see by. The nearest stars are light years away, their light too faint to illuminate this darkness. But if you could see, you'd witness something extraordinary. The cloud is enormous, perhaps a light year across, containing enough material to form our sun, all the planets, all the asteroids and comets and dust that fill our solar system today. And throughout this vast cloud, water ice is everywhere. Not in the dramatic forms you know, no glaciers, no icebergs, no snowflakes, just molecular coatings on dust grains, perhaps a few dozen molecules thick. Frost in the darkness, patiently waiting. The cloud is rotating, very slowly, so slowly that a single rotation takes millions of years. But this rotation matters, as the cloud slowly collapses under its own gravity, pulled inward by the combined mass of all its particles. The rotation speeds up. Conservation of angular momentum, the same physics that makes a figure skater spin faster when pulling in their arms. Watch this collapse happen. We'll speed up time now, watching millions of years pass like hours. The cloud flattens, becoming a disk. Most of the mass falls toward the center, where it will eventually ignite as the sun. But the outer regions remain relatively cold, relatively dispersed, forming what will become the protoplanetary disk. The water ice on those dust grains travels with them. In the inner solar system, close to the forming sun, the increasing heat vaporizes the ice. Water molecules are torn from their dust grains, floating free as gas. But farther out, beyond what will become Mars's orbit, it remains cold enough for ice to persist. This creates a boundary, invisible but crucial. Astronomers call it the frost line or ice line, the distance from the sun where water can condense from vapor to ice. Inside this line, water remains as vapor. Outside this line, ice can exist. The frost line isn't a sharp boundary, but a gradual transition, and it moves over time as the young sun's output varies. But roughly, it lies somewhere between the orbits of what will become Mars and Jupiter. This positioning will prove crucial for Earth's water story. Let's focus now on the region beyond the frost line, where ice can exist. Here, dust grains coated with water ice begin to stick together when they collide. The ice acts like glue, helping particles adhere to each other. Slowly, over thousands of years, these particles build up into larger clumps, pebbles, then boulders, then small planetesimals a few kilometers across. Each collision is gentle, almost tender. In the near vacuum of the protoplanetary disk, there's no air resistance to cause heating, no violent impacts, just soft, gradual accumulation. A boulder drifts through the disk at a few meters per second. It encounters another boulder. They touch. The ice on their surfaces, slightly sticky at these cold temperatures, holds them together. They're now one object, twice as massive, with twice the gravitational pull to attract other objects. This process, accretion, continues across millions of years. The larger objects grow faster, since their greater gravity attracts more material. Gradually, the protoplanetary disk sorts itself into distinct regions. Close to the Sun, where only rock and metal can remain solid, small rocky planets begin to form. Farther out, beyond the frost line, objects can incorporate ice along with rock, growing much larger. Watch a comet nucleus forming. Start with a single dust grain, perhaps 1/1000th of a millimeter across, coated with water ice just a few molecules thick. It collides with another grain. They stick. Now it's twice as large. More collisions follow, dozens, hundreds, thousands. After 10,000 years, it's grown to the size of a pebble. After 100,000 years, a boulder. After 1,000,000 years, a mountain. The growing comet nucleus is not solid ice, not like an ice cube. It's a loose agglomeration of material, dust grains, small rocks, frozen water, frozen carbon dioxide, frozen methane and ammonia, all mixed together in a matrix that's more like compacted snow than solid ice. The structure is porous, full of tiny spaces between particles. If you could hold it, it would crumble like a very old, very cold dirt clod. All around the outer solar system, thousands upon thousands of these objects are forming. Most remain small, meters to kilometers across, but they're numerous, filling the region beyond the frost line with icy debris. This is the source material for the comets that will, eventually, bring water to Earth. But that's getting ahead of the story. First, the planets must form. Watch now as Jupiter begins to dominate the outer solar system. Jupiter forms quickly, within a few million years, because beyond the frost line, there's so much more solid material available. Ice is abundant, and Jupiter's core grows massive enough to gravitationally capture hydrogen and helium gas from the surrounding nebula. She becomes enormous, over 300 times Earth's mass, her gravity reshaping the entire outer solar system. Jupiter's gravity stirs up the icy bodies beyond the frost line. Their orbits become more eccentric, more inclined. Some are flung inward toward the Sun. Others are thrown outward, some gaining enough velocity to escape the solar system entirely. Jupiter acts like a giant gravitational slingshot, flinging icy bodies in all directions. Some of these bodies, countless trillions of them, are thrown into the far outer reaches of the solar system, where they settle into a vast spherical cloud surrounding the Sun at distances of thousands or tens of thousands of astronomical units. This is the Oort cloud, a reservoir of comets that will persist for billions of years, occasionally sending members back to the inner solar system when stellar encounters or galactic tides perturb their orbits. Others settle into a flatter disk beyond Neptune's orbit, the Kuiper belt. Here they remain, cold and pristine, preserving the chemical composition of the primordial solar nebula, almost unchanged for billions of years. But some, a small fraction, but still numerous in absolute terms, are flung inward, toward the inner solar system where Earth is forming. Let's follow one such object now. A comet nucleus perhaps 5 kilometers across, a loose conglomeration of ice and dust and rock. It's been drifting in the outer solar system, slowly accumulating material. But Jupiter's gravity has perturbed its orbit. Now it's falling sunward, beginning a journey that will take thousands of years, but will end at Earth. As it falls inward, the comet accelerates, gaining speed from the Sun's gravitational pull. It passes Saturn's orbit, then Jupiter's again, then Mars's. The Sun grows brighter in its sky. Though there's no sky really, no atmosphere to scatter light, just the black of space and the growing brilliance of the Sun. The comet begins to warm. The Sun's heat, still faint at this distance but stronger than anything the comet has experienced before, starts to sublimate the ice on its surface. Water molecules break free from the solid, turning directly to vapor without passing through a liquid phase. There's no air pressure here to allow liquid water to exist. A thin haze of water vapor begins to surround the comet. Its coma. The vapor is quickly ionized by solar ultraviolet light, and the solar wind, the stream of charged particles flowing outward from the Sun, pushes it into a tail stretching millions of kilometers behind the comet, always pointing away from the Sun. But the comet's interior remains frozen. Only the outermost layers sublimate. The comet is losing mass, leaving a trail of water vapor and dust along its orbital path, but its core remains intact, for now. The comet crosses Earth's orbit. Earth is still forming, still accumulating material, but she's already substantial, perhaps a third of her final mass. The comet's path intersects Earth's path. They're not at the same place at the same time. Space is vast, and even though their orbits cross, the chance of actual collision is small. But this comet is just one of thousands, millions, all being thrown into the inner solar system by Jupiter's gravitational perturbations. Some will impact Earth. Others will strike Venus or Mars or the Moon. Many will pass by, eventually either crashing into the Sun or being flung back out to the outer solar system or beyond. This process, the delivery of icy bodies from the outer solar system to the inner planets, continues for hundreds of millions of years. It's most intense during the first 100 million years of the solar system's history, but it continues, gradually declining. Throughout the late heavy bombardment we discussed before, each impact delivers water. A 5-kilometer comet might contain a few trillion tons of water ice, a smaller comet proportionally less. The impacts are violent, the kinetic energy is enormous, but water molecules are robust. Many survive the impact. Even if the ice vaporizes from the heat, the vapor spreads into Earth's atmosphere, eventually cooling and condensing as rain. Imagine now the Earth during this era of heavy bombardment. Her surface is still largely molten, but it's cooling, forming a crust. The atmosphere is thick with water vapor, carbon dioxide, nitrogen, gases brought by impacts and volcanic outgassing. The sky is perpetually overcast, thick clouds covering the entire planet. And then, as Earth cools below the boiling point of water, something remarkable begins to happen. The water vapor in the atmosphere starts to condense, not as gentle rain, but as a deluge. A planetary, scale rainstorm that may last for thousands of years. The rain falls on hot rock, instantly turning back to steam, rising back into the atmosphere to condense and fall again. But gradually, the surface cools enough for water to remain liquid. Pools form in low-lying areas. They grow into lakes, then seas. The first ocean basins begin to fill. Not all of Earth's water comes from comets. Much of it was present in the original rocky material that formed Earth, water molecules chemically bound into minerals, released by volcanism as Earth's interior heated and melted. But comets contributed significantly, perhaps 30% of Earth's total water inventory. The exact fraction is still debated by scientists, but what's clear is that water arrived by multiple paths, over hundreds of millions of years, gradually accumulating to form the oceans we know today. Let's slow down time again now. Let's rest in this vision of water accumulating, drop by drop, impact by impact, volcanic eruption by eruption, water patient and persistent, finding its way to Earth through 1,000 different paths. Picture the first permanent ocean, shallow and global, covering much of the planet's surface. The water is hot, near boiling in many places. It's acidic from dissolved carbon dioxide. It's full of dissolved minerals from contact with fresh volcanic rock. It's utterly lifeless, sterile, unable to support any organism as you know them. But it's water, liquid water. And in this water, chemistry begins to happen. Complex molecules form, stabilized by the aqueous environment. Amino acids, the building blocks of proteins. Nucleotides, the building blocks of DNA and RNA. Lipids that can form membranes, creating boundaries between inside and outside. We're getting ahead of the story again. We're still in water's youth, its early days on Earth. But rest now in the knowledge that water has arrived. The long journey from the solar nebula, through the cold outer solar system, delivered by countless comets and asteroids and volcanic gases, has brought water to Earth. And water, once arrived, never leaves. It cycles, ocean to atmosphere to land and back to ocean. But the total amount remains roughly constant. The same water molecules have been here for over 4 billion years, recycling endlessly through different forms and different vessels, but never departing entirely. You carry some of those ancient molecules in your body right now. Water that was once part of comets. Water that fell as rain on primordial Earth. Water that has passed through countless living things before you. Water that connects you to the deepest history of the solar system. Breathe slowly. Let this ancient water flow through your awareness. Feel yourself part of this long, patient story. Rest now, as water rests in the ocean, waiting for the sun to lift it back into the sky to continue its endless cycle. Let's focus now on a specific moment in Earth's history. Though, moment is relative when we're speaking of events that unfold over millennia. We're going to witness the transition from a dry, volcanic world to a planet with oceans. The event that transformed Earth into the water world we know today. The time is approximately 4 billion years ago, though the exact timing is still debated among scientists. Earth is roughly 150 million years old, ancient by human standards, but still an infant planet. The Theia impact that formed the Moon happened perhaps 100 million years earlier. The surface has cooled considerably since then, but it remains a harsh, alien environment. Picture Earth from space at this moment. She's smaller than she will be, still accumulating material, still growing through impacts. Her surface glows faintly red in places, where the crust is thin and the molten interior shows through. Volcanic activity is intense, with thousands of volcanoes active simultaneously, their plumes creating a thick, murky atmosphere. The atmosphere itself is nothing like today's. No oxygen, that will come much later, billions of years in the future, as a product of life. Instead, the air is mostly nitrogen, carbon dioxide, water vapor, and smaller amounts of methane, ammonia, and sulfur compounds. The pressure is higher than today, perhaps twice as high. All this gas pressing down on the surface, and the temperature. This is crucial to our story. The temperature is dropping. The surface has cooled from thousands of degrees to hundreds of degrees. The critical threshold approaching is 100 degrees Celsius at sea level pressure, the boiling point of water. The atmosphere is saturated with water vapor. Absolutely saturated. So much water vapor that it accounts for perhaps 30% of the atmosphere's mass. This vapor comes from multiple sources: comets vaporized on impact, asteroids containing water, bearing minerals, and especially from volcanic outgassing as Earth's interior melts and releases gases trapped in rock. Every volcanic eruption adds more water to the atmosphere. The magma rising from Earth's mantle contains dissolved water, like carbonation in a soda bottle. As the magma reaches the surface and pressure drops, the water flashes to steam, exploding outward in volcanic plumes that carry it high into the atmosphere. Imagine standing on this early Earth, though you couldn't, not without protection that doesn't yet exist. The sky above is completely obscured by clouds. Not the white, fluffy clouds you know, but thick, dark, oppressive clouds extending from near the surface to the upper atmosphere. The sun is completely hidden. The light that reaches the surface is a dim, diffuse glow, barely bright enough to see by. The landscape around you is volcanic rock, sharp, black basalt, still warm to the touch. Lava flows snake across the terrain, glowing orange and red. The air is thick, humid, hard to breathe even if you could breathe it, which you couldn't. The composition would be toxic to any modern organism. And then, you feel the first drop. It's not cold. How could it be, with the surface temperature still above 100 degrees Celsius? The water vapor cannot condense into liquid at these temperatures. But wait. Watch as the surface continues to cool. The cooling happens gradually, unevenly. Some areas cool faster than others. Highland regions, farther from active volcanic zones, cool first, and in these regions, the temperature drops below that critical threshold. The water vapor in the atmosphere, so long held as gas, begins to condense. It doesn't happen all at once, and it doesn't happen everywhere simultaneously. But where it does happen, it's dramatic. The condensation releases latent heat, the energy that was holding the water molecules apart as vapor. This heating warms the surrounding air, creating updrafts, generating the first weather systems, the first wind patterns. Clouds begin to form in a new way. Not just vapor hanging in the air, but actual liquid droplets suspended by air currents. These droplets collide, merge, grow larger. Eventually they become too heavy for the air to support. Rain begins to fall. Imagine witnessing this first rain. The drops are large, heavy, falling fast through the thick atmosphere. They fall onto hot rock and instantly flash back to steam with a hissing sound that echoes across the landscape like a million serpents. The steam rises, condenses again, falls again, a cycle establishing itself, precipitation and evaporation, over and over. But the surface continues to cool. Each rain shower, even though it evaporates immediately, carries heat away from the surface. The rock temperature drops 95 degrees, 90 degrees, 85 degrees, and eventually, in some places, the temperature drops low enough that the water doesn't entirely evaporate. A puddle forms. Just a small pool in a depression in the rock. Steam rises from its surface. It's still near boiling, but it persists. More rain falls. The puddle grows, becomes a pond, then a lake. This process repeats across the planet. In every low-lying area, in every crater, in every valley between volcanic ridges, water begins to accumulate. The rain continues, perhaps for centuries, perhaps for millennia. We don't know exactly how long the Great Rain lasted, but geological evidence suggests it was long, thousands of years at minimum, possibly much longer. Let's speed up time now, watching this process unfold. The isolated lakes and ponds begin to merge as water levels rise. They overflow their basins, water flowing downhill, carving the first rivers through the fresh volcanic rock. The rivers connect lakes into chains, then into vast inland seas. The rain continues. Always the rain. Falling from those perpetual clouds, drumming on the surface with a sound like distant thunder. The water is hot, too hot for any life as we know it, and acidic from dissolved carbon dioxide. It reacts vigorously with the basaltic rock, dissolving minerals, carrying them into solution. The water begins to take on the chemistry that will, eventually, make it suitable for life. Watch as the first ocean basin begins to fill. The topography of early Earth is different from today. No continents as we know them, just vast expanses of volcanic crust, with varying elevations. The lowest areas are essentially enormous craters, impact basins left over from the late heavy bombardment. These begin to fill first. Water flows into these basins from all directions. Rivers, temporary at first, but becoming permanent as the rain continues, carry water from the highlands. The basin fills slowly but steadily, a meter per year perhaps, or even slower. But with thousands of years passing, the water depth grows to hundreds of meters, then kilometers. The first ocean is born. It's smaller than any of Earth's modern oceans, confined to one large basin, but it's substantial. Deep enough that its bottom layers remain liquid even as surface layers evaporate. Large enough that waves begin to form. driven by the first true winds as heat differences create pressure gradients in the atmosphere. Let's descend beneath the surface of this primordial ocean. The water is murky, full of suspended particles, dust from continuing impacts, volcanic ash, minerals dissolved from rock. Visibility is poor, perhaps only a few meters. The temperature decreases with depth, near boiling at the surface, perhaps 50 or 60 degrees Celsius at the bottom where the pressure is greater. The ocean floor is volcanic rock, fresh and unweathered. In some places, hydrothermal vents are forming. Cracks in the crust where seawater seeps down, is heated by contact with magma, and rushes back up in superheated plumes. These vents are chemical factories, creating exotic minerals and providing energy that will, much later, support entire ecosystems. But for now, the ocean is sterile. No life anywhere. Just water and rock and dissolved chemicals, slowly equilibrating, slowly finding their chemical balance, above the ocean. The rain continues, though less intensely now. Most of the water vapor has condensed out of the atmosphere. The clouds are thinning. For the first time in millions of years, breaks appear in the cloud cover. Sunlight reaches the surface in shafts of dim light, illuminating the gray, green ocean and the black volcanic landscape. The rain doesn't stop entirely. The hydrological cycle is now established. Water evaporates from the ocean surface, rises into the atmosphere, condenses into clouds, falls as rain, flows back to the ocean. This cycle will continue, with variations, for the next 4 billion years. It continues today. It will continue long after humanity is gone. But the intense deluge of the great rain is over. The ocean has formed. The water has found its equilibrium. Let's rise up now, above the atmosphere, to view Earth from space. The transformation is striking. Where once there was only volcanic rock and impact craters, now there's a blue, gray ocean covering perhaps a quarter of the planet's surface. The clouds are thinner, patchier, allowing the surface to be visible. She looks more like the Earth, though still strange. The continents haven't formed yet. There's no plate tectonics as we understand it today. The crust is uniformly thin, uniformly volcanic. But there's water, liquid water on the surface, an ocean. This ocean will grow. More comets will impact, delivering more water. More volcanic eruptions will release more water from the interior. Over the next 100 million years, the ocean will expand until it covers most of the planet, a global ocean, perhaps interrupted by volcanic islands and small highland regions, but continuous, deep, truly planetary in scale. The presence of liquid water changes everything about Earth's evolution. Water is a solvent, allowing chemistry to happen that cannot occur in solid rock or thin atmosphere. Water moderates temperature, absorbing heat during the day and releasing it at night, evening out extremes. Water transports materials, cycling elements between ocean and atmosphere and rock, and water eventually will enable life. Not yet. We're still hundreds of millions of years too early for life. But the stage is being set. The ocean is the crucible in which life will form, the medium in which it will evolve, the environment that will shape every living thing that ever exists on Earth. Think about what we've witnessed. Water vapor, invisible in the atmosphere, condensing into droplets, droplets merging into drops, drops falling as rain onto hot rock, steam rising, condensing, falling again, puddles growing into ponds, ponds into lakes, lakes into seas, seas into an ocean. A transformation from a dry, hostile world to a water world. The most important transition in Earth's history, enabled by the simple physics of phase changes, water transitioning from gas to liquid as temperature drops. It seems almost mundane when described that way. Just condensation, just precipitation, processes you see every time it rains. But this was the first rain, the rain that created Earth's oceans, the rain that made our world habitable. Rest now in that knowledge. Every time you see rain, you're witnessing an echo of that primordial deluge. Every ocean you look upon is a descendant of that first ocean. Every drop of water you drink has cycled through Earth's systems for billions of years, but it all traces back to this moment, the Great Rain. when water finally found its home on Earth. Let yourself drift now, like a raindrop falling through ancient clouds, like a river flowing toward the primordial sea. Let the rhythm of rain, the patient accumulation of water, lull you into deeper relaxation. There's more of water's story to tell, but for now, rest here, at the moment when Earth's oceans were born. Come forward now through time, billions of years, to the present, to laboratories where scientists work quietly, patiently, teasing out the secrets of ancient water from some of the oldest materials on Earth. This is detective work on a molecular scale, reading clues written in crystal structures and isotopic ratios, reconstructing a history that no one witnessed, and that left only the faintest traces. Let's begin with zircon. Not the cubic zirconia of jewelry, that's synthetic, but natural zircon, zirconium silicate, one of the most remarkable minerals on Earth. Imagine yourself in Western Australia, in a region called the Jack Hills. The landscape is arid, scrubby, red, brown earth baking under intense sun. Ancient metamorphic rocks outcrop here, worn smooth by billions of years of weathering. To the casual observer, these rocks appear unremarkable, but they contain treasures, tiny crystals, most smaller than a grain of sand, that hold secrets from Earth's earliest days. These are zircon crystals, and some of them are over 4 billion years old, among the oldest materials ever found on Earth's surface. Most rocks from that era have been destroyed, recycled by plate tectonics, melted and reformed countless times. But zircons are nearly indestructible. They resist weathering, resist melting, survive being incorporated into younger rocks. They're time capsules, preserving chemical signatures from the moment they formed. Watch now as a geologist carefully extracts rock samples from the outcrop, bags them, labels them with meticulous care. The samples are transported to a laboratory, where they're crushed and processed. The zircon crystals separated from surrounding material, using density separation techniques and magnetic separators. Under a microscope, the zircons are beautiful, tiny translucent crystals, some yellow, some brown, some colorless, all with the characteristic elongated shape and pyramid, like terminations of zircon's crystal structure. But their beauty is incidental. What matters is what they contain. Each zircon crystal grew from molten rock, magma, as it cooled and crystallized. As the crystal formed, it incorporated certain elements into its structure, while excluding others. Zirconium and silicon, obviously, they form the crystal's basic structure, but also trace amounts of uranium and thorium, which substitute for zirconium in the crystal lattice because they have similar chemical properties. This uranium is crucial. Uranium is radioactive, slowly decaying to lead over billions of years. By measuring the ratio of uranium to lead in a zircon crystal, scientists can determine exactly when that crystal formed. Radiometric dating, precise to within a few million years, even for crystals billions of years old. But there's something else these ancient zircons can tell us. Something even more remarkable. They can tell us about the presence of liquid water on early Earth. Watch as a researcher carefully mounts a zircon crystal. This one, dated to 4 billion years old, formed just 150 million years after Earth itself, and analyzes its oxygen isotope ratios using a sophisticated instrument called a secondary ion mass spectrometer. Oxygen exists in 3 stable isotopes: oxygen-16, the most common, oxygen-17, rare, and oxygen-18, less common than oxygen-16 but more abundant than oxygen-17. The ratio of oxygen-18 to oxygen-16 in a material depends on the conditions under which it formed. Here's the key insight: when magma interacts with liquid water, the oxygen isotope ratios change in distinctive ways. Water-rich environments produce characteristic isotopic signatures that are preserved in minerals that crystallize from that magma. The 4 billion year old zircons from Jack Hills show these water interaction signatures. Their oxygen isotope ratios indicate that the magma they crystallized from had interacted with water, liquid water, at Earth's surface. This is remarkable evidence. It tells us that liquid water existed on Earth's surface by 4 billion years ago, perhaps even earlier. This was controversial when first proposed in 2001. Many scientists believed early Earth was too hot for liquid water, a magma ocean, that took hundreds of millions of years to solidify. But the zircons don't lie. Their isotopic signatures are clear. Liquid water existed on early Earth, much earlier than previously thought, possibly within just 150 million years of the planet's formation. Let's shift now to a different line of evidence, a different way of reading water's history. We're going to look at deuterium, heavy hydrogen. Most hydrogen atoms consist of just a proton and an electron. But about 1 in every 400 hydrogen atoms in Earth's water is deuterium, heavy hydrogen, which has both a proton and a neutron in its nucleus. This makes water molecules containing deuterium slightly heavier than normal water molecules. The ratio of deuterium to normal hydrogen in water, written as DBH ratio, varies depending on water's history. Different sources of water in the solar system have different DDH ratios, like chemical fingerprints indicating their origin. Picture a laboratory now, at NASA's Goddard Space Flight Center or a similar institution. Scientists are analyzing water samples from various sources: Earth's oceans, Antarctic ice cores, water extracted from meteorites, measurements of comets taken by spacecraft. They're building a database. Comet Halley, measured when it passed near Earth in 1986, has a DH ratio about twice as high as Earth's ocean water. Comet Hale-Bopp, measured in 1997, similar twice Earth's ratio. For years this was puzzling. If comets delivered Earth's water, why don't the DDH ratios match? But then, measurements of other comets reveal more diversity. Comet Hartley 2, measured in 2010, has a DDH ratio very close to Earth's ocean water. Comet 67P Churyumov of Gerasimenko, visited by the Rosetta spacecraft in 2014, has a ratio 3 times Earth's, even higher than Halley. The picture becomes clearer. Not all comets have the same DDH ratio. It depends on where in the solar system they formed, what temperatures they experienced, how much their ice sublimated and recondensed during their history. Comets from the Kuiper belt have different ratios than comets from the Oort cloud. What about asteroids? For a long time, scientists couldn't directly measure water in asteroids. They're small, distant, and don't develop the spectacular coma and tails that make comets easy to study. But meteorites, fragments of asteroids that fall to Earth, can be analyzed in detail. Certain types of meteorites, called carbonaceous chondrites, contain water locked into their mineral structure. Not liquid water, but hydroxyl groups, oak, chemically bound into the crystal lattices of clay minerals. When these meteorites are gently heated in the laboratory, this water is released and can be analyzed. The DH ratio in carbonaceous chondrite water is remarkably close to Earth's ocean water, much closer than most comets. This suggests that asteroids, not comets, may have been the primary source of Earth's water, but it's more complicated than that. Computer models of the early solar system suggest that both asteroids and comets contributed. Perhaps 60 to 70% of Earth's water came from asteroids, with the remainder from comets. The exact proportions are still debated, but the evidence increasingly points to asteroids as the dominant source. Let's look at another line of evidence. Ancient rocks that once were submerged beneath ancient oceans. We're in Greenland now, on the southwestern coast, examining rocks from the Isua Greenstone Belt. These rocks are 3.8 billion years old, among the oldest well-preserved sedimentary rocks on Earth. Sedimentary rocks formed from sediments deposited by water, which means these rocks are direct evidence of ancient oceans. A geologist kneels beside an outcrop, examining the rock texture with a hand lens. The rock is metamorphosed. It's been heated and compressed over billions of years, altering its original structure, but its sedimentary origins are clear. You can see layering, the remnants of ancient seafloor deposits. Chemical analysis of these rocks reveals they formed in the presence of liquid water. They contain minerals that only form in aqueous environments. They show evidence of chemical weathering, the process by which water breaks down rocks and transports dissolved materials. These rocks tell us that by 8 billion years ago, Earth had stable oceans. Not just transient pools or temporary seas, but long-lived oceans that persisted long enough to deposit thick sequences of sediment. Oceans deep enough and stable enough to create the geological formations we see today. There's even more tantalizing evidence in some of these ancient rocks. Certain chemical signatures suggest the presence of life, microbial life, by 8 billion years ago, perhaps even earlier. The evidence is controversial, debated, not universally accepted. But if true, it means life arose very quickly once liquid water was present, within just a few 100 million years of the Great Rain. Let's examine one more line of evidence, this one from an unexpected source: the Moon. Apollo astronauts brought back samples of lunar rock between 1969 and 1972. For decades, scientists assumed these rocks were completely dry. The Moon has no atmosphere, no liquid water, no way to retain volatile compounds like water. Early analysis seemed to confirm this. The lunar samples appeared bone dry, containing no water whatsoever. But in the 2000s, using more sensitive analytical techniques, scientists discovered traces of water in the lunar samples. Not much, just a few parts per million, but it's there, locked into volcanic glass beads and mineral grains. This water likely came from the Moon's interior, released during volcanic eruptions billions of years ago. But where did the Moon's interior water come from? Remember, the Moon formed from the debris of the Theia impact. That debris came from the mantles of both Earth and Theia, vaporized and then recondensed. If the Moon contains water, it means both Earth and Theia had water in their interiors at the time of collision. This pushes water's presence on Earth even earlier, back to the very formation of the planet. Water wasn't just delivered later by comets and asteroids, it was present from the beginning, incorporated into the rocky material that accreted to form Earth. The picture that emerges from all these lines of evidence, zircon crystals, deuterium ratios, ancient sedimentary rocks, lunar samples, is one of water arriving by multiple pathways over an extended period. Some water was present in the original material that formed Earth, locked into minerals, released by volcanism as the planet's interior melted. Some arrived via asteroids from the inner asteroid belt, objects that form just beyond the frost line and contain substantial water ice. Some came from comets, icy bodies from the outer solar system flung inward by gravitational interactions with the giant planets. The delivery continued over hundreds of millions of years, but the bulk of it happened early, within the first few 100 million years of Earth's history. By 4 billion years ago, liquid water existed on the surface. By 8 billion years ago, stable oceans had formed. And possibly by the same time, life had already begun. This detective work continues. Every new meteorite analyzed, every new comet measured, every ancient rock formation discovered adds to our understanding. The story becomes more detailed, more nuanced, more complete. But the essential narrative is established: water came to Earth from space, delivered by countless impacts over vast stretches of time, gradually accumulating to form the oceans that cover 70% of our planet's surface today. Think about the patience required for this scientific work, analyzing microscopic crystals one atom at a time, measuring isotopic ratios to incredible precision, dating rocks with accuracy of just a few million years out of billions, building an understanding grain by grain, measurement by measurement, paper by paper, over decades of careful research. It mirrors water's own patience. Water that waited billions of years in the cold outer solar system before beginning its journey to Earth. Water that accumulated drop by drop, impact by impact, eruption by eruption, until the oceans formed. Water that cycled through Earth's systems for billions of years, patient and persistent, never rushing, never ceasing. Rest now in the knowledge that this research continues. That laboratories around the world are carefully, methodically, reading the history written in ancient materials. That each measurement, each analysis, each discovery adds another piece to the puzzle of water's origin. Let yourself drift like water seeping through rock, patient and unhurried, finding pathways through stone grain by grain. Let the slow pace of geological research, the careful accumulation of evidence, lull you into deeper relaxation. The story is being written, slowly but surely, in the quiet patience of scientific investigation. Come back now, fully to the present. To your comfortable space, your quiet moment, your connection to water in its most familiar forms. Let's contemplate what it means to live on a water world, to be a water-based organism on a planet where water shapes everything. Climate, geology, biology, civilization itself. You are, essentially, a temporary container for water. Your body is approximately 60% water by weight, closer to 75% for an infant, dropping to about 50% in old age, but always predominantly water. Your brain is 73% water. Your lungs, 83%. Your blood, which carries oxygen and nutrients to every cell, is 90% water. Every cell in your body exists in a water-based environment. Each cell is like a tiny ocean, enclosed by a membrane, with complex chemistry happening in aqueous solution. Water is not just present, it's essential, participating directly in countless biological processes. Proteins fold into their functional shapes because of how they interact with water molecules. DNA's double helix is stabilized by water. Every chemical reaction in your body happens in water, or because of water. You lose water constantly. Every breath you exhale carries water vapor. Every time you sweat, urinate, even digest food, you're losing water. An average adult loses about 2.5 liters per day, more in hot weather or during exercise. This water must be replaced, constantly, or your body begins to fail. After just 3 days without water, most people would die. Think about that dependency. You can survive weeks without food, but only days without water. Your body has elaborate mechanisms for conserving water, concentrating urine, reducing sweat production, triggering thirst. But these are temporary measures. Fundamentally, you need water, constantly, to remain alive, and you're fortunate, extraordinarily fortunate, to live on a planet where water is abundant and accessible. Consider what this means in practical terms. Turn on a tap, and clean, drinkable water flows out. Open a refrigerator, and cold water awaits. Walk outside when it rains, and water falls from the sky, free, replenishing rivers and reservoirs and groundwater. This abundance is unusual, even unique, in the solar system. Let's contrast Earth's water wealth with other worlds, to appreciate just how fortunate we are. The Moon, our closest neighbor, has traces of water ice in permanently shadowed craters at the poles, perhaps a few 100 million tons total. This sounds like a lot, but Earth's oceans contain 1.4 billion trillion liters of water. The Moon's water resources are minuscule by comparison, and accessing them would require mining ice from crater floors that never see sunlight, in one of the most hostile environments imaginable. Mars has water, but most of it is locked in polar ice caps or frozen in the soil as permafrost. The atmosphere is so thin and cold that liquid water cannot exist on the surface. It would either freeze or evaporate instantly. A human on Mars would need to extract water from ice or soil, melt it, purify it, carefully budget every drop. Water would be precious, carefully recycled, never wasted. Venus once had water, probably oceans early in her history, but lost it all. The runaway greenhouse effect raised surface temperatures above 450 degrees Celsius. Any remaining water is trapped as vapor in the thick atmosphere, or chemically bound in surface rocks. Venus is a cautionary tale of what happens when a water world loses its water. The gas giants Jupiter, Saturn, Uranus, Neptune contain water in their atmospheres, but in forms we cannot access. Water exists as vapor in their upper atmospheres, as liquid droplets in deeper cloud layers, perhaps as exotic high-pressure ice in their deep interiors. But there's no surface to stand on, no ocean to draw from. Their moons are more promising, Europa, Enceladus, Titan, but even these are covered in ice kilometers thick, with liquid water oceans hidden beneath. Earth is special. Liquid water on the surface, stable over billions of years. Temperatures in the range where water can exist as solid, liquid, and gas, allowing the water cycle to operate. Enough water to cover most of the planet, but not so much that all land is submerged. An atmosphere that holds moisture, but allows precipitation. It's a remarkably narrow set of conditions, and Earth occupies that narrow zone almost perfectly. This is sometimes called the Goldilocks zone, or habitable zone, the distance from a star where temperatures allow liquid water on a planet's surface. Too close, and water evaporates, leading to a runaway greenhouse effect like Venus. Too far, and water freezes permanently, like Mars. Earth orbits in the middle just right. But it's not just Earth's distance from the Sun that matters. The planet's mass is crucial, large enough to hold onto an atmosphere but not so large that it becomes a gas giant. The presence of the Moon, stabilizing Earth's axial tilt and creating tides. The magnetic field, protecting the atmosphere from being stripped away by solar wind. Plate tectonics, cycling water between surface and interior. All these factors work together to maintain Earth as a water world. Let's think about how water shapes your daily life, often in ways you don't notice. You wake up in the morning and shower, using perhaps 50 to 100 liters of water, heated to comfortable temperature, flowing over your skin to clean away oils and dead cells. This simple act, which you might spend 15 minutes on without thinking, would be impossible on any other world in the solar system. On Mars, it would consume a significant fraction of a day's water budget. On the Moon, it would be unthinkably wasteful. You make coffee or tea, water boiled and infused with plant compounds. You drink it slowly, enjoying the warmth, the flavor, the caffeine. You're consuming water, but water transformed, enhanced, made pleasurable. The ability to use water not just for survival, but for enjoyment is a luxury made possible by abundance. You eat breakfast. Almost everything you eat contains water. Fruits are 80 to 90% water, vegetables similar, even bread is about 35% water. The plants this food came from grew using water absorbed from soil. Water that fell as rain, that evaporated from the ocean, that cycled through the atmosphere. Your breakfast represents the end point of numerous water cycles. Water repeatedly used and reused to grow food. Throughout the day, you're surrounded by water without thinking about it. The air you breathe contains water vapor, more on humid days, less on dry days, but always present. This humidity moderates temperature, makes air feel warmer or cooler than the thermometer indicates, affects how quickly sweat evaporates from your skin. If you live near the ocean, that massive body of water moderates your climate. Coastal areas have milder temperatures than inland areas at the same latitude, because water heats and cools more slowly than land, creating a buffering effect. The ocean absorbs heat during summer and releases it during winter, evening out seasonal extremes. Even if you live far inland, water shapes your weather. Storms form when moist air rises and condenses. Rain falls when atmospheric conditions allow water droplets to grow large enough to overcome air resistance. Snow forms when temperatures are low enough for water to crystallize directly into ice. Every weather event you experience is fundamentally about water changing phase, moving through the atmosphere, redistributing heat and moisture. Consider the infrastructure required to provide you with clean water. Reservoirs storing water from rain and snowmelt. Treatment plants removing contaminants and pathogens. Pipes distributing water to millions of buildings. Pumps maintaining pressure. All of this exists because water is abundant enough to justify the infrastructure, but still precious enough to require careful management. In many parts of the world, this infrastructure is less developed or absent entirely. Billions of people lack access to clean, running water. They must walk to wells or rivers, carry water home in containers, carefully ration what they collect. They're more aware of water's value because they interact with it more directly, because obtaining it requires effort. But even in these circumstances, Earth's water abundance is evident. There are wells to dig, rivers to draw from, rain to collect. Water is available, even if accessing it is difficult. Compare this to living on Mars, where water would have to be extracted from ice or soil, purified extensively, recycled religiously. Earth's water scarcity, where it exists, is about distribution and infrastructure, not fundamental shortage. Let's think about water in Earth's larger systems. The way it connects everything, cycles endlessly, makes this planet uniquely dynamic. The water cycle, also called the hydrological cycle, is beautifully simple in concept. Water evaporates from oceans, lakes, rivers, and soil. It rises into the atmosphere as vapor. It condenses into clouds. It falls as precipitation, rain, snow, sleet, hail. It flows across land in rivers, seeps into groundwater, collects in lakes, eventually returns to the ocean. Then the cycle repeats. But within this simple framework, endless complexity. Some water cycles quickly. A rain shower followed by rapid evaporation, returning to the atmosphere in days. Other water moves slowly, groundwater seeping through rock layers, taking decades or centuries to return to the surface. Glacial ice can store water for thousands of years. Some water molecules currently in the ocean might not evaporate again for millennia. The total amount of water on Earth remains essentially constant, about 1.4 billion trillion liters. But it's constantly moving, constantly changing form, constantly cycling through different reservoirs. The ocean holds about 97% of it. Ice caps and glaciers hold about 2%. Groundwater, lakes, rivers, atmosphere, and living things together hold the remaining 1%. You are part of this cycle. The water you drink becomes part of your body temporarily, but it doesn't stay. You excrete it as urine, sweat it out, breathe it out as vapor. That water returns to the environment, is treated and purified. If you live in an area with sewage treatment, eventually makes its way back to rivers and oceans, evaporates, falls as rain somewhere else, perhaps is drunk by someone else or absorbed by plants or evaporated again. The water molecules in your body right now have been cycled countless times. Some were once part of dinosaurs. Some fell as rain on ancient civilizations. Some were drunk by historical figures you've read about. Some have been cycled through the ocean dozens of times since you were born. Water connects you to all of Earth's history, to every organism that ever lived, through this endless cycling. Think about how water moderates Earth's climate globally. The ocean is an enormous heat reservoir, absorbing solar energy during summer and in the tropics, releasing heat during winter and at high latitudes. Ocean currents transport this heat around the planet. The Gulf Stream carrying warmth to northern Europe, the Kuroshio Current moderating East Asian climate. Without these currents, temperature differences between equator and poles would be far more extreme, making much of the planet less habitable. Water's high heat capacity, the amount of energy required to change its temperature, is crucial here. Water resists temperature change more than almost any other substance. This is why coastal areas have milder climates than inland areas, why islands have remarkably stable temperatures, why the ocean takes months to warm in summer and cool in winter, while land responds within days or weeks. Water also regulates temperature through evaporation. When water evaporates, it absorbs heat from its surroundings. This is why sweating cools you down, why the air feels cooler near fountains or waterfalls, why evaporative coolers can reduce temperature without refrigeration. On a planetary scale, evaporation from the ocean continuously removes heat from the surface and transports it into the atmosphere, where it's released when the vapor condenses into clouds and rain. Even Earth's geology is shaped by water. Water weathers rock, breaking it down through chemical reactions and physical processes. Water transports sediment, carving valleys, building deltas, shaping coastlines. Water, seeping deep into the crust at subduction zones, lowers the melting point of rock and enables volcanism. Water in soil and rock affects how earthquakes propagate. The presence of subsurface water influences where minerals concentrate, where geothermal energy can be accessed, how the crust responds to stress, and of course, water made life possible. The first organisms evolved in water. life remained exclusively aquatic for billions of years, roughly 3 billion years, before venturing onto land. Even land organisms are fundamentally aquatic. We carry ocean-like fluids within us. Our cells are tiny water-filled capsules. We require constant water input to survive. Every ecosystem on Earth depends on water. Rainforests exist where rainfall is abundant. Deserts exist where it's scarce, though even deserts have life adapted to extract every possible drop from fog, dew, or rare rains. Rivers create ribbons of fertility through arid lands. Wetlands support incredible biodiversity. The ocean itself is Earth's largest ecosystem, containing the majority of the planet's biomass and most of its biodiversity. You are part of this water world, this planet where water is the essential substance, the connector, the enabler of everything you know. Every aspect of your existence depends on water's abundance, its unique properties, its constant cycling through Earth's systems. Rest now in that knowledge. Feel the water in your body, the fluid in your cells, the blood flowing through your veins, the moisture on your breath. You are a temporary part of water's long journey, a brief eddy in the endless current that connects all life on Earth. Think about the water you'll drink tomorrow. It's been cycling through Earth's systems for 4 billion years. It fell as part of the Great Rain. It has been ocean water and river water and rain, and snow and ice and vapor and groundwater, and plant sap and blood and sweat and tears. It has supported countless organisms, weathered mountains, carved canyons, filled seas, evaporated into clouds, fallen as rain again and again and again. And now, for a brief moment, hours, days, it will be part of you. Then it will continue its journey, cycling onward, patient and persistent, as it has for billions of years, and will for billions more. Let yourself relax into that timeless current. Let the knowledge of water's journey, from comets to oceans to you, settle over you like a gentle rain. Breathe slowly, feeling the water vapor entering and leaving your lungs with each breath. Feel your connection to the ancient oceans, to the primordial rain, to the comets that delivered this precious substance to our world. You are safe here, on this water world, surrounded by abundance, protected by the same water that has sustained life for billions of years. The water cycle continues, endless and reliable, providing what you need without thought or effort on your part. Rest now. Let sleep come like rain falling on quiet ground, like water seeping into soil, like rivers flowing peacefully to the sea. Let yourself drift into the gentle current of rest, knowing that water, patient, persistent, essential water, will still be here when you wake, cycling endlessly, sustaining all life, connecting you to the deepest history of Earth and the solar system. Sleep now, water-based organism, on your water world, in the gentle embrace of H&O molecules that have traveled billions of years and billions of miles to make your existence possible. Rest. Drift. Sleep. The story of water is the story of Earth itself. From the cold depths of the solar nebula to the warm ocean lapping at sandy shores. From ice on ancient comets to rain falling on your roof. From the great rain 4 billion years ago to the glass of water on your nightstand. Water is patient. Water is persistent. Water never truly leaves, it only changes form, moves through cycles, connects all things across time and space. You have traveled with water tonight, through its ancient history, through its transformation from cosmic ice to planetary ocean. You have witnessed its patience, its power to shape worlds, its essential role in creating and sustaining life. Now let that journey end, here, in this quiet moment. Let the rhythm of water, waves on shores, rain on leaves, rivers flowing to the sea, carry you into peaceful sleep. The water will still be here tomorrow, cycling endlessly, as it has for billions of years. For now, rest in its embrace, part of the great current that connects all life on this water world we call home. Good night. Sleep well. Let the ancient waters carry you gently into dreams.